again for coming to my PhD defense, especially to all the jury's member. It's a great honor to talk about the 3 years of my work with experimental researchers like you. And as this long title suggested, we're going to talk about extended reality learning environments and their effect on cognitive load and curiosity. But just before using complex words, let me introduce the key concept of my research with a short story. Here is Suzanne, and like every young people, she was scrolling on Instagram when she came across a post that caught her attention. In France, strokes are responsible for over 30,000 deaths each year. And intrigued by this information, she wanted to learn more and Googled strokes and found this brief definition: a stroke is a brain injury that can cause death. Not really satisfied by this superficial information, she clicked on the first link, scientific article, and tried to read it, but the information was too hard to understand, very complex, with a lot of words, no images, and no pictures, so she didn't understand nothing. And she then remembered that her best friend Leo told her about his new educational tool, the virtual reality headset, allowing to interact with the human brain. So she went to his place to try it, and after a long minutes to set up the virtual reality headset, and people who already use this type of devices know what I mean, she found herself in a virtual classroom in front of a virtual brain, and she could interact with it and even cut arteries to get information about stroke and better understand what it is. And the animation and audio explanation helped her to understand. And so beyond this anecdotal stories, Suzanne's behaviors reveals fundamental insights about the cognitive mechanisms involved in human learning. First, when Suzanne discovered the impact of strokes on population, it triggered a sense of curiosity, a sense of questioning to know more about this information. And according to learning progress hypothesis, this internal need to know that we call curiosity is characterized by a loop between the identification of a knowledge gap, a phase of seeking of information to fill this gap, and the arising of new questions from the last and new knowledge acquired by the learner. And in addition, this motivation to seek information is driven by the expectation of a reward resulting from the new knowledge acquisition. And more precisely, when we perceive that we made progress in our knowledge, what we call learning progress, the brain produces a positive signal that we interpret as reward. And just as sugar pushes us to more food, this internal reward stimulates our curiosity and pushes us to keep exploring and learn the more possible. And the particularity of this intrinsic reward, as the name suggested, is that it's not a tangible or external one. It's an internal sense of satisfaction that arises when we fill the gap. And it reflects what we call intrinsic motivation, the internal desire to learn that comes from within, in opposition with extraneous extrinsic motivation, like external reward and money, for example. Then we can define curiosity as the intrinsic motivation to learn, driven by the learning progress perception. According to self-determination theory and according to learning progress hypothesis, intrinsic motivation not only depends on perceived learning progress, but also on what we call autonomy or agency. So I need to feel that the progress in my knowledge is the result of my own action to be intrinsically motivated and curious. And so when Suzanne read on Google that stroke is simply a brain injury, the information was too superficial, she didn't learn nothing, and then she didn't feel any intrinsic motivation in the reward. Later, when she tried to read the scientific paper, it was the opposite extreme, it was too complex, she couldn't make sense of it, and then no perceived learning, no intrinsic motivation to continue to understand the scientific article. And this aligns with Vygotsky's of proximal development, suggesting that to maximize learning progress, the task should fall between too easy and too difficult, what we try to do with virtual reality. Another major educational theory that can help us to understand the student's behavior is cognitive learning theory. And it suggests that learning, like any cognitive task, requires cognitive resources in working memory that we call cognitive load. And so the more complex the task, the higher the cognitive load. And the specificity of this cognitive load theory is that it distinguishes between two types of load, intrinsic load and extraneous load. So intrinsic load refers to the mental effort required to process the inherent complexity of the task. So typically here, resolving a simple linear equation requires less intrinsic cognitive load than resolving a more complex one. And in the student case, the complex scientific article requires higher intrinsic load than the simple definition. It's also important to say that this intrinsic cognitive load depends on the prior knowledge of the learner. Like, for example, for me, resolving this simple equation requires less intrinsic load than a 9-year-old learner who never heard about this equation. And maybe another example, someone with strong math skills might immediately recognize that the apparently complex equation is in fact easier than the linear one because all the terms cancel out and the equation is always true. The other type of load is called extraneous cognitive load, and it refers to the amount of mental effort required to deal with elements not directly relevant with the learning task. For example, how the information is presented or structured. So here, for the water cycle, we have the same information, the same complexity of the task, so the same intrinsic load, but the diagram requires less extraneous load than the text, especially if the text is very hard to read like this one. And we can do a parallel with the scientific article in the virtual reality. And so in other words, intrinsic load refers to the content of the information, while extraneous cognitive load more on the format, how the learning task is presented. All right, so we just seen that coming information requires cognitive resources in working memory, but cognitive load theory also suggests that creating knowledge from this information requires cognitive resources, what we call German cognitive load. And so in other words, transferring the relevant information from working memory to long-term memory require cognitive load that we call German. Maybe we see it. And so German cognitive load can be interpreted as the level of cognitive load the level of cognitive engagement and motivation we put to actively process and encoding the information in long-term memory. And now, I hope yes. And so according to this both theories, so cognitive load theory and intrinsic motivation frameworks, a well-designed learning task should provide adaptive difficulty by minimizing irrelevant cognitive load, irrelevant information if necessary, and also maximize progress, learning, and autonomy to enhance intrinsic motivation, curiosity-driven behavior, German cognitive load, and then learning. And this is the central challenge in 21st century education, to support learners in exploring complex information without overloading them, and to transform this curiosity into meaningful learning. And to address this challenge, extended reality has emerged as a promising tool. So we can define extended reality as all immersive technology that blend real and physical and digital elements. So there is two most common forms: augmented reality, where we keep the visualization of the physical world, but we integrate digital information on it. And for example, we keep the visualization of the classroom, but we add digital, and we can interact with digital information into this physical world. And the other one, virtual reality, immerses the user in a completely virtual and digital environment. And that's what Suzanne's used, for example. And so today, education is one of the main application domain of extended reality. And many companies are investing in these technologies, especially because of their potential to enhance intrinsic motivation and engagement. And actually, this is the origin of this thesis. We talked to it this morning with Florian. They saw a growing interest for projects with augmented reality and virtual reality for the learning, but especially due to the attractiveness of this new technology. But they needed to learn and to know to better understand under what condition with which features this technology can truly enhance learning and enhance intrinsic motivation and cognitive growth. And so this is precisely the first goal of my thesis. To answer this question, what are the instructional features of this technology that can optimize learning, and to explore the underlying cognitive mechanisms through cognitive load and curiosity that can help us to understand these technologies. So as I said before, one of the main arguments from the company for using this technology is this potential to enhance intrinsic motivation due to its immersive and engaging nature. But when we look at the literature, what we did with the systematic review on 35 papers, even if we showed that the majority of the study demonstrated a positive impact of extended reality on intrinsic motivation, this higher motivation did not translate into better learning. This is what we can see here. And so, despite challenge expectation from self-determination theory and curiosity-driven learning frameworks, that's why we qualified it as inconsistent. And we identified that this inconsistent results were mostly due to misconception in what we call intrinsic motivation, and also due to methodological issues regarding the way intrinsic motivation was measured. The systematic review also revealed that there is some differences in how virtual reality and augmented reality impact cognitive load. So we show that the majority of the study reported a negative effect of virtual reality on cognitive load and learning of participants, while we show that augmented reality tends to reduce extraneous cognitive load by adding relevant information and help students to understand. And it was particularly true for novice learners, because when we look at the participants with more prior knowledge, we show the opposite trends with those learners that not benefit from augmented reality, but benefit more from virtual reality. So we show an expertise reversal effect among the studies, including in this systematic review. In addition, even if intrinsic motivation and cognitive load are among the most studied cognitive factors in educational psychology over the last 35 years, especially in extended reality community, they are often considered separately, and despite the intuitive connection between motivational frameworks and cognitive load theory, further work is needed to better understand how it can interact. And this is precisely the second objective of my thesis, to try to relate both cognitive load theory and intrinsic motivation frameworks, and to explore if the combination of this both framework can help us to understand the effect of these technologies on learning. And so this is the conceptual frameworks we developed and that guided how this thesis experimental works. So as you can see, we try to relate cognitive load theory and learning progress hypothesis, and we also assess how it can, the variation and the effect of extended reality on this integrative model. Regarding the design and methods, all along this thesis, we focused on the concrete and cognitively demanding learning domain, the raw anatomy. We started from the typical way anatomy is taught, and we used a video I recorded during a lesson by Dr. Ligoro. I don't know if she is here with us, but who presented the vascular system of the brain. And I hope the video will work.
Avec ce qu'on vous appelez gouttière vasculaire, ce qui va passer l'artère. Ensuite, ici, la moelle allongée au bulbe, la fissure médiane, les pyramides et les ombilicaux. Et ici, la limite avec la moelle spinale, c'est l'os occipital qui est donc le foramen magnum. Donc, moelle allongée pont, et ici, le mésencéphale avec les deux pédoncules cérébraux.
So it's hard to see, but the video presented Dr. Ligoro using drawings to explain the different arteries of the brain. And The video lasts 20 minutes and introduces all the major brain arteries and their function, territories, and the consequences of a stroke on it. And as you may see, she used drawings to support her explanation, and the students, the participants, were expected to reproduce this complex drawing in a real time. And so it's an extremely demanding cognitive task because students must process a continuous flow of information, stay focused on Dr. Ligoro's explanation and information, and in the same time replicate the drawing in time pressure and with limited drawing skills. And so this constitutes our control video to follow the 20-minute video and to reproduce the drawing at the same time. And we also deliberately prevented the participant to pause the video to match the traditional learning situation. To support the drawing task and reduce its cognitive complexity, we also developed two augmented reality systems that project an overlay of the anatomical structures into the paper sheet, enabling the student to trace directly over the outline. And I hope the video will help you to understand the technology we use. So the first one was an augmented reality system based on the Poupard technologies, Poupard software, using a projector to display the drawing guide into the paper, helping the student to draw. And also the student can use keyboard to switch of overlays and to follow the teacher's drawing. We also replicate this system using Microsoft HoloLens, so a headset that projects the overlay just above the eyes, making the task quite differently, but with the same principle, as you can see here. And we also implemented the last version of this HoloLens technology, this time including a 3D brain, a 3D representation of the anatomical structure we used, allowing the user to interact with it and to better understand the spatial relationship between this anatomical structure. I hope you can understand. Okay, so for summarize, the task was similar than the control condition. So to follow the lesson and to draw at the same time, but this time with the augmented reality assistance, and for the last condition, with also at the same time the exploration of the 3D representation of the brain. To support neuroanatomy learning in virtual reality, we also developed a virtual reality application that reproduces a classroom-like setting, displaying a 3D model of the brain at the center. And so the learner can interact with the virtual brain. I'll try to use again a video. So the learner can use hand tracking to touch the brain, even touch arteries to get information, the same information from the control video, but this time with animation and oral explanation, and also cut arteries to get information about the consequences of a stroke. So each interaction triggers verbal explanation and animation, and a virtual tablet offers the written summaries of this explanation. And the content was designed in collaboration with an anatomy teacher to align with the lesson video to remain pedagogically consistent throughout the condition. And so the task, the virtual reality task, also lasted the same amount of the time, about 20 minutes. We also implemented three different levels of interactivity, three versions of this virtual reality application. The first one, the active one, where the participant could freely interact with the 3D brain. The guided one, where the participant keeps the possibility to interact with the brain, but this time with no choice about the sequences of the action. And the last one, the passive one, where the user can't interact with the 3D brain, which is more closer to the control condition. And so we use the same procedure to evaluate these technologies. So we use a pre-post test design with a measure of knowledge on anatomy before and after the task. And we also use standardized questionnaire on cognitive load, motivation, and user experience to improve it. And so yes, as I said before, curiosity is defined as the motivation, the intrinsic motivation to learn. And so we use questionnaire about motivation, intrinsic reward, and things like this to characterize curiosity. When I used intrinsic motivation, I talked about curiosity. The theses were conducted in quasi real-life conditions with 1 to 8 participants at the same time in 2 different universities, Nîmes and Bordeaux. And we collected data from about 300 participants from the 2nd to the 5th years of medical study. Sorry, there is a picture for the setting, but anyway. Yeah. And so there is 4 experimental contributions in this thesis works. The first one is the exploration of supporting drawing with augmented reality here. Then the exploration of the levers of interactivity for virtual reality. And then we replicated the study to get more data to explore the links between behavioral data, the behaviors of the participants into the virtual reality environment and our subjective measure of cognitive load and curiosity, and also to validate the structural equation modeling or conceptual modeling. And so I propose you to present this for the main result for this 4 experimentation. All right, so for the first one, the augmented reality condition, when we compare control condition with 3 types of augmented reality supports for drawing, the analysis revealed that hopefully guiding support the learner in the driving task, make them the task easier, and we showed improved driving accuracy for the 3 augmented reality supporting conditions. But they didn't include more elements nor in the driving nor of the legend, more legends, suggesting that even if the driving task was easier with augmented reality, they didn't push them to draw more. We also found a significant higher intrinsic motivation in 3 augmented reality supporting driving conditions compared to control condition. And we also showed that the condition with the projector and the last one with the 3D brain, in this condition, participants reported lower extraneous cognitive load. So if I summarize, support drawing with augmented reality helps students to draw better, enhance their intrinsic motivation, and reduce for some conditions their extraneous cognitive load, but we didn't find any differences on learning performance. And so one explanation could be the too high level of guidance we provide. As you remember, maybe, we provide a complete, a full overlay of the structure. So it for sure reduces the external demand of the task, but it also reduces the generative properties of the driving task. So we cancel the positive impact of driving by giving a full support of the driving. And this is supporting by the lack of difference on German cognitive load we found between the participants. We also can again question the effect of the higher intrinsic motivation in all the technological conditions on learning. And when we try to explore the relation between intrinsic motivation and learning between each condition, even if we saw a positive trend between for the majority of conditions, for the last one, the condition with a 3D brain, we found that the most motivated participant reported lower learning, which is very weird. And so we can suppose that the addition of the model distracts the learner from the main learning task, and or that this higher intrinsic motivation for the participants were more directed into interact and play with the system than more to understand what the Dr. Ligoro said. Regarding the virtual reality experiments, we showed that the passive condition, so with no interaction, and the active condition with freely exploration of the brain reported higher knowledge acquisition than the control group. We again also show that all the technological virtual reality conditions show higher intrinsic motivation and also self-determination, so more curiosity than control condition, but that the overall perceived cognitive load was constant across the groups. But when we look at the repartition of this cognitive load, we show some different trends across the condition. So for example, we show lower extraneous cognitive load than for the passive guided and active condition compared to control, here in red, with a higher German cognitive load for the 3 conditions compared to the control condition. So the overall cognitive load was similar across condition, but the repartition were more optimal in the virtual reality condition. And so this is not really coherent with our systematic review that revealed that the most of the study showed an addition of extraneous cognitive load with virtual reality. But remember that in this experiment, the control task was very highly cognitively demanding with multiple tasks, and using virtual reality maybe have students focus on essential elements by deleting the dual task associated with drawing. And also, we know that in anatomy, understanding the spatial relationship between the anatomy structures and also the spatial representation of these structures is very important, is essential. And so providing a 3D and spatial representation of their structures in virtuality maybe help students to understand and then promoting German cognitive load. The second objective of this experiment was also to explore the difference between interactive levels with some assumption, for example, for the active cognition of more curiosity-driven learning because there is freely exploration, but we didn't find any differences on any of our indicators between the 3 virtual reality conditions, maybe suggesting that in this specific case, interactivity is not the main factor to explain the positive effect of extended reality, or maybe we talked about it with Julia this morning too, that the interaction was not really relevant regarding the learning task. That's it for this experiment. During this virtual reality exploration, we also recording the behaviors of the participants into the virtual reality environment. And specifically, we recorded the distance traveled by the head and the hands into this virtual environment, and also the frequency of rapid movement the participant did during the experiments. And we showed that the hands movement negatively predicted intrinsic motivation, maybe suggesting that the higher hands movement reflect disengagement or parasite movements. We also, in contrast, we show that the head movements were more related to curiosity and cognitive engagement, German load, maybe suggesting that the seek information and exploration is more through the head in this particular setup than with the. We also recorded exploration behavior through through 2 indicators. So virtual environment exploration rate, so the quantity of exploration of the participants, and also we measured entropy of the movement, so the diversity and variability of this movement into the virtual reality environment. And we showed that the participants with higher entropy reported higher intrinsic motivation, curiosity, and higher cognitive engagement, and lower motivation, suggesting that more exploratory behaviors and curiosity could be assessed with this entropy. On the contrary, we found that participants with the high rates of movements and exploration were not the most curious participants, suggesting that more accurate measure and characterization of the curiosity of participants is more through the diversity of the movement than the quantity of this movement. All right, and also all along this thesis, so through all the experiments with augmented reality, with virtual reality, across all our subjective measure of intrinsic motivation and curiosity, but also across our behavioral data that we discussed just before, we found that the more motivated students reported lower extraneous cognitive load, here in red, and we also found a strong positive relation between motivation and German load. So we show relation between cognitive load theory and motivation. And to go further, this result, we tested this relation with structural equation modeling. And specifically, we demonstrated a strong negative effect of the result showed a strong negative effect of extraneous cognitive load on perceived learning progress, but no direct effect of this irrelevant cognitive load on intrinsic motivation, maybe suggesting that the negative effect of cognitive load theory on intrinsic motivation is more through the perception of learning progress than the direct effect on intrinsic motivation. We also, contrary to our expectation, didn't find any interaction between intrinsic load and intrinsic motivation, and one reason may be the lack of variation in intrinsic difficulty across the condition. And finally, again, we didn't find a positive and direct effect on intrinsic motivation on learning gain that make echoes with what we said before in the distraction effect of the augmented reality. We also confirmed the positive effect of autonomy and agency on intrinsic motivation, and interestingly, contrary to our expectation, we found that autonomy reduced extraneous cognitive load, suggesting that self-regulation not always impose additional extraneous cognitive load, but also can reduce it if the task is well calibrated to participant skills level. And finally, I don't have the time to detail these results, but we also found some differences in our extended reality impact this relation. That, for example, we show that only virtual reality promote agency, then intrinsic motivation, and so reducing extrinsic motivation. So if I summarize the main takeaways of this PhD work, we found with the first study that augmented reality and mixed reality can enhance driving precision and driving accuracy of the participants with promoting curiosity and reducing extraneous cognitive load, but we found that maybe this higher interest motivation were not really directed to true learning, but more on exploration and entertainment. And we also show that the excessive guidance providing with the augmented reality may reduce and even cancel the positive effect of the driving task. With the virtual reality, we show that it improves learning of anatomy by enhancing curiosity and reducing extraneous cognitive load, but we didn't find any differences between the interactive levels, raising some question about the effect of interactivity on learning performance. And we also demonstrated some connection between the behavior of participants in the virtual reality environments with the subjective measure of cognitive load and motivation. But the lack of direct visualization of what the participants did during the experiment limits us in the interpretation of this connection and these results. And finally, as I said just before, we found some connection between curiosity frameworks and cognitive load theory, especially through the negative effect of extraneous cognitive load on perceived learning progress. And we found that, an effect of extended reality affordance on this connection and this model. Of course, there is some limitation regarding this work. So, despite the quite large sample size we use for the studies, it's still small given the high numbers of conditions of our experiments, and we also only included medical students. So include a more broader sampling would be help us to understand the effect of these technologies. And similarly, learner expertise, and we also talked about it with Julia this morning, also emerged as a critical factor to explain the effect of extended reality on learning. So for example, in the systematic review, we showed this reversal effect according to the learner expertise, learner prior knowledge. And despite our effort to include participants with different study level, so we include participants from the 2nd to the 5th years of medical study, the prior knowledge of these participants remains relatively homogeneous. So again, exploring these technologies in more broader sampling and with participants with different expertise, level of expertise can help us to understand more these technologies. As you see, a notable trend into these works was the difficulty to show the direct effect of intrinsic motivation on learning, and one explanation could reside in the only short-term and post-test measure of intrinsic motivation we include in our protocols. So we can expect that the positive effect of intrinsic motivation could manifest more in long-term, sustaining engagement and deep learning over the time. And also, according to this limitation of long-term measure, there are still some answered questions about the long-term effect of extended reality on learning. And so, also according to the industrial context of this thesis, it could be a good idea to go further and try these technologies on more longitudinal context and more longitudinal studies. Also, we only use a 20-minute task for the virtual reality to respect the recommendation about the health recommendation about the virtual reality using, but it's limiting us to understand if a more long session can help us to better understand. Similarly, even if we use quasi-real-life context, even if you try to reproduce quasi-real-life context, it's still controlled experiment with experimental methodology that differ notably from the typical education, and also, again, considering the industrial context of this thesis, it's very important to validate these technologies and to explore the use of these technologies in more real-life context with more students, etc. One of our ambitions in this thesis was to explore how extended reality could support diverse types of learning, and July advised me at the beginning of the thesis that it was maybe a bit too optimistic, and so we didn't have the time to explore the effect of this technology on procedural learning. But yes, according to training simulation literature, extended reality may be particularly effective in supporting procedural learning, and so exploring the effect of these technologies on procedural learning could be a good idea. We talked about, for example, using augmented reality for medical intervention training. And also, this is also true for the industrial context of this thesis, to try to find how these technologies can be positive in more general context, in different type of learning, and to continue to develop and to assess these technologies in different contexts, to understand and better implement it in real-life context of learning. And finally, as many studies in educational psychology and cognitive load, one limitation is that we relied mainly on subjective measure of intrinsic motivation and cognitive load. And even if we try to use other data, such as the behaviors of participants during the virtual reality exploration, the results remains preliminary, and we had to go further for this result. And the promising direction could be to combine this measure with more objective measure, like physiological measure, like EEG, for example. Regarding the next steps, we can go further for the question about learning progress hypothesis and cognitive load theory in third place. For example, in curiosity-driven learning literature, we show the quadratic relation between task difficulty and motivation, and we can do the parallel between this task difficulty and intrinsic load. And we can maybe ask some question about, is it the same trend with extraneous cognitive load, or is it only a linear one, as we demonstrated in this thesis? And so we can imagine to use Flowers Lab and curiosity-driven frameworks and adapt it to cognitive load theory to investigate this question in more diverse educational contexts and also larger cohorts. Similarly, Flowers' team works on algorithms that target activities which provide the higher learning progress to maximize curiosity based on learning progress hypothesis and then zone of proximal development. But we know that zone of proximal development is a null theory and based on few empirical proof, and such recent works show some difficulties to target the appropriate level of difficulty for participants. And so maybe cognitive theory can help us to define this zone of proximal development and then more accurately target the task with the best level of difficulty. And finally, we know that metacognition is a critical factor in both curiosity frameworks and cognitive theory, and so investigate this this metacognition can maybe help us to understand the relation between curiosity and cognitive load. And thank you for your attention. I hope you understand something, even in the video, even with the bugs. And thank you very much. Thank you also for the contributors of this work.